Welcome to springlib.
Let's start with an observation. Let's write the first number, so 1, 2, 3, and let's highlight the squares. So 1, 4, 9, 16, and so forth. Now, let's transform this sequence by applying the floor of the square root of the number. So we have, well, root of 1 is 1 and the floor is 1. Then root of 2 is 1 point something and the floor is 1. Root of 3 is 1 point something and the floor is 1. And then when we go to 4, when we take the root, that's exactly 2, so the 4 is going to be 2, and so forth until we reach root of 9, which becomes 3, and so forth. Where let me highlight the corresponding numbers in green here. So you see that every time we go to a square, then the floor of the square root goes up by 1. Now let's count how many of these numbers are there. So 3 ones, 5 twos, and you can compute that there are 7 threes, and so forth. So it looks like there are odd numbers of numbers which are the floor of a root. And why is that? Because let's say that we're taking a number m, which is between a square, let's say n squared, and the following squared. So for instance, if m were 6, then 6 would be between 4 and 9. So n would be 2 and 3. And in fact, in this case, well, 2 is between the root of 6, which is 2 point something, and n plus 1, which is 3. And the root of, well, the floor of root of 6 would be exactly 2 in our case. So all the numbers m between n squared and n plus 1 squared are such that the floor of the square root is exactly n. And, well, there are exactly n plus 1 squared minus n squared, which is equal to 2n plus 1, such numbers m. So for instance, if n is 2, we're counting the numbers between 2 squares of 4 and 3 squared 9, and there are exactly 5 such numbers. So okay, let's remember this. And now we want to compute this sum. We want to compute the sum for k that goes from 0 to m of the floor of root of k. So let's split this sum into, well, we sum all the way from k to n squared minus 1 of floor of root k plus the remaining numbers. So k goes from n squared to m of floor of root k, where this number big N is such that, well, is the last perfect square before m. So if m were 6, again, n squared will be 4. All right. So now that we have this information, we can look at the first sum, and we know how that behaves because, well, we have 3 ones, then we have 5 twos, and we go all the way up to n plus 1, which we sum a number of times, and the number of times is exactly twice n minus 1 plus 1. And that's the first sum. And then for the other sum, well, we know that the floor of the root of k is exactly n. So this is n summed a bunch of times, and this number of times is exactly m minus n squared. And this is the second part, where we have the crucial observation that n big N is exactly the floor of root of m. All right, now it's just a matter of writing these sums in a more suitable way. So the sum in green, well, let's write it as a sum over j. J goes from 1 to n minus 1 of, well, there are 2j plus 1 such numbers, and every number is worth exactly j. And this is the sum in green. And then we have the sum in red, but that's just m minus n squared that multiplies big N. All right, now let's linearize the first sum. So that's twice the sum of j squared plus the sum of j, where j goes from 1 to n minus 1. But now we have formula for these sums. This is n minus n squared that multiplies n plus, well, we use the formula for the sum of squares, which we multiply by 2, so we have a denominator of 3. And then the other sum is n minus 1 that multiplies n divided by 2. And again here, big N is just a shorthand for floor of root of m. And this is the formula that we wanted.